Hello everyone. Today we will talk about the question 1 of homework 10. And the question 1 asks us to define this following process. The first one is the Poisson process. The definition of Poisson process is for the number n from t1, t2 of the point ti in the interval of t1, t2 of the length t delta t, which is equal to t2 minus t1, is a Poisson random variable with parameter lambda t. As for the equation is y as the following format. Here is the definition of the Poisson process. And the first definition and the second definition of a Poisson process is if the interval t1 and t2 and t3 and t4 are non-overlapping, then the random variable n t1, t2, this one, and the n t3, t4 are independent. Also, at a time moment t, there's no more than one Poisson point. Using the point ti, we form the stochastic process. As for when we draw the graph, which looks like this. And the first order probability maxes for the Poisson process looks like this. Looks like this in here. And the mean of the Poisson process looks like this. Autocorrelation is equal to this one in here. And the autocovariance is equal to this part in here. Also, we can write this form as clearly, more simply, as this one. And for the second process is a Poisson increment process. The definition is yt equal to this part in here divided by the epsilon. And the first order probability masses is equal to this equation. And the mean of the Poisson increment process is in here is equal to this one. And the autocorrelation t1, t2 is equal to two parts. The first part is when t1 minus t2 greater than epsilon. And the second part looks like this. t1 minus t2 divided by epsilon squared and t1 minus t2. And the autocovariance is equal to this part in here. T1 minus T2 divided is kind of similar to the autocorrelation. So now let's look at the point impulse process. The point impulse process is defined as Ct equal to this one. In here, the xt is a Poisson process. The graph looks like this. And the probability maxes is no definition, and the mean is equal to lambda, and the autocorrelation t1, t2 is equal to this part right here. And the autocovariance is C T1 T2 is equal to this part. Now let's look at the semi-random telegraph signal. In here, the xt is defined based on the Poisson point again. The number n t1, t2 of the point ti in the interval t1, t2 of length t equals to t2 minus t1 is a Poisson random variable with parameter lambda t. So when we write it down, for the semi-random telegraph signal is equal to this equation here. And the xt is defined as 1 and -1 when k is even in 0 to t, k is odd in 0 to t. And the first order probability message is equal to this one in here. And the mean is equal to this part. And the autocorrelation T1, T2 is equal to this thing. And the autocovariance T1, T2 is equal to this part in here. Now let's look at the random telegraph signal, which is defined as y t a x t and the p. In here, the xt is a semi-random telegraph signal. And for the first order probability message is equal to this equation in here. And the mean is equal to 0. And the autocorrelation T1, T2 is equal to this part. And the autocovariance C T1, T2 is same as the autocorrelation. Now let's look at the random walk. The definition of random walk is like when we toss a fair coin n times, k is the number of heads in n tosses. For the equation, when we write it down, it looks like this. And the first order probability message function is equal to this point here. When we expand this equation a little bit, it looks like this when t belongs to this range, and the mean is equal to 0. And the autocorrelation T1, T2 in this case is equal to the mean S squared. And the autocovariance T1, T2 is also equal to this part. And now let's look at the Wiener process. The definition looks like this when we write the equation form. In here, the xt is the random walk. And the first order density function looks like this part in here. And the mean is equal to 0 as well. And the autocorrelation T1, T2 is equal to mean T1, T2 times alpha. And the autocovariance T1, T2 is same as the autocorrelation. And that's much how we prove those prove the definition for this process. And thanks for listening.